Let me show you how to take the derivative of logarithm with an arbitrary base b. Here b is going to be any fixed number that's bigger than 0. We know how to take the derivative of the natural log. That's when b is equal to Euler's number e. So how do we do this? There's basically two different ways, and the first way is through implicit differentiation. That's what I'll show you right now. What we can do is we can take this equation, and if I exponentiate both sides, I can look at b to the y, and I can look at b raised to the power of log b of x. And given that those are inverse functions, it's just going to give me x. And so then implicit differentiation would say, okay, now if you know the derivative of the function b to the y, you'll be able to solve this problem. And since we have learned the derivative of b to the y in the previous video, that's what we'll do. So what I can do here is I want to use the chain rule to take this derivative as usual. What I'm going to get is the derivative of b to the y, that's natural log of b times b to the y. That's the derivative if I were taking the derivative with respect to y. But since I want to take the derivative with respect to x, right, I want to find dy dx. So you get that derivative. I have to use the chain rule with b to the y as my outside function and y equals f of x as the inside function. So you take the derivative, plug in y, and then multiply by y prime. And then that's going to be equal to the derivative of x with respect to x. And that gives you 1. So solving for y prime, we end up with 1 over natural log of b times b to the y. And as usual, we'd like to rewrite this in terms of x. And how can I do that? Well, I know that y is equal to log with base b of x. So b to the y then has to be nothing but x. And we saw that here already. So that's our derivative of natural log with base b of x. The way you get it is just 1 over x, and then you're also dividing by natural log of b. There's another way to think of this. There's another way to conceptualize it. I said there's two ways to think about that derivative. If I wanted to do this directly, without using implicit differentiation, I would just have to remember that if I want to take, looking at this function y, if I want to take y prime, then the way to do that, it's the reciprocal of the derivative of the inverse function. And the inverse function is b to the y. That's something that's good to remember. It always helps you find the derivative of the inverse function no matter what. And then when you do this, either way, you end up needing to know the derivative of the inverse function. And when you do this and write down the formula, that's natural log of b times b to the y. And you're not using the chain rule here because you're really just taking the derivative of this function and then at the point y. That's different from what we did over there when we had to take the derivative of that function, but we were plugging in y equals f of x. So notationally they look the same, but what's going on under the hood is a little bit different. And here I just, using the same argument, natural log of b, and b to the y is just equal to x. So either way you do it, you end up with the same answer, although one argument you're thinking as y is a function of x. With this argument, you're thinking that the specific point y is fixed, just taking this derivative as usual and then plugging that in.